Hello, my name is Scott Gillespie, and I'm here to deliver the workshop on strategic tillage and soil carbon. I wish I could be there in person, but some things have come up that's not going to let me be there, so I have recorded the presentation so that everyone can still learn and bring things back to their farm. So we're going to get going on this. Okay, so to begin, I'm going to put up this fine print because there's always fine print in anything that we do. Anything that we talk about or discuss with others, always check with your certifier before changing or make sure that it fits into your rules. Keep up with organic rule and regulation changes because there could be things that, although sometimes it can seem like there should be no problem using it, but you just want to err on caution on this here. Another thing is that soil science has never moved more rapidly than it does now. There are new tools and techniques that have developed in the last few decades that have just revolutionized what can be done. And so there's been a lot of changes, a lot of work on things that people could not see in the past. It's mostly on the molecular level, or at least in the very fine sensing, because there's a lot of things that were going on that could only be observed with experiments, but now can be seen at a much deeper level. Even then, soil science, if you think about it, is a very tough thing to work on because you're dealing with something that you can't see, you can't go into, and as soon as you try to go into it, you disturb what is going on. So it is something that is changing. There's a lot going on in it. So yeah, there's just been a lot of new information in the last few decades. There has been a lot of investment in it for its climate change potential, and so that has also driven a lot of change in it. But it has also driven some opposing theories that will clash in public, or at least if you're in this world or if you're watching what's going on. There are opposing theories of what can and can't be done with the soil, and or what, especially when it comes to carbon capture. There are fairly heated debates out there, and so that is something that I have seen, and I guess debate is healthy, but sometimes some people are set that must be acted on right away, even if things aren't, the science isn't complete, whereas other people are putting some caution into what should be done, and that is what is happening. So the bottom line is that what I understand now is bound to change. And what I'm hoping to bring to this workshop is the stuff that's more practical, the stuff that you don't have to understand at a deep level, or have to try to understand a bunch of different theories or ideas. It's stuff that we can bring home to the farms right now. Now, before we get too far into this is a workshop. It's not a lecture. Now, unfortunately, the way, if you are watching it through the recording, it is going to be more of a lecture. I would have hoped to have had it more question and answer based or interactive, but it doesn't mean that what can be done too is the video, the presentation can be paused and questions can be asked, or group discussion can still happen. So I'm still going to be presenting the information. It has to be lecture style, but it still is a workshop, and there are opportunities within it to work together, and a larger project at the end where everyone can be working with each other on developing some solutions for your farms. So that is how it is going to be. Now, the difference about today and about how things were when I first started going to conferences and meetings in the late 90s is that we have internet now, and we can look things up later. We can refer to details later, or we can go into more in depth on things, or we can even keep conversations going later. When I was first starting to go to things, that was it. You had to go to the conference to learn things. You had to listen to somebody speak. Even in terms of printed material, you had to get it there, or you had to go to. I grew up in Ontario, so there were centers, or there was ag centers, and you had to pick up fact sheets physically, or you had to pick up or buy books physically. So we don't have to bring a whole bunch of stuff with us for you to take home, and there's so much information out there. But what I have did is I've put together a resource with links in it for further reading. There'll be a way for you to access it, or if you want it printed, you can let us know, though most of it is links to go to places, so to look up more information. So the electronic form is probably going to be your best bet, though I have found with some new updates on my iPhone, I'm not sure how it works with Android, but actually the camera system can actually recognize links and send me right to the links. So that is an option if it's a printed thing. So this is the time together. Let's use the time well. We want to have discussion, and then, as I said, the last half hour is about working together. So I want to take you back in how I learned about soil organic matter. You will see this SOM throughout the presentation. Always remember that's soil organic matter, or wherever it's you see OM, that's organic matter for the acronyms. So when I was in school, I went to the University of Guelph for my agriculture degree, and what I learned was the way that organic matter was formed or was created was there's the plant fungal or plant fauna microbes. They were either living or dead. So we have the living creatures or the living plants out there doing their thing. So that is organic matter. And then there is the dead, which obviously are the ones that have recently died or been eaten. And that is what is running through our system. And so obviously after a harvest, we have a lot of dead material out there, and then it's up to the living fauna, which could be all the insects or earthworms or whatever, to break it down into smaller things, and then the microbes work at breaking that down. And then what we have was called the very dead. And this was considered our long-term organic matter, this humic substances. And there wasn't a lot known about them. The main thing was that they were supposedly these very large, complex molecules that had been created from the breakdown of material, and that these are what were our long-term organic matter that could be decades, or maybe more like centuries or millennia old. Now, what has happened in the last 10, 20 years since I was in school is that there has been a lot of work on or a lot of new techniques, as I had mentioned earlier, learning about or being able to look more at what these molecules are. And what it appears has happened is that these don't actually exist in soil. So it seems like it was more of an artifact of the extraction process when they were studying organic matter. And so as the soil science advanced, there were people that were putting out ideas that it was the humic substances didn't actually exist. And it turns out that this has been a debate within soil science even up to 100 years ago, where people were thinking it didn't quite make sense, but they couldn't look any deeper. And there's some who say that realistically, as microbes break down material, and when they use different structures, or they use different molecules for energy, it really should be making less complex molecules, not making more complex molecules. So when extraction is happening, or when we're trying to measure organic matter, there's chemicals that are used that are around pH 13, which is very, very high on the pH scale, which is very close to bleach. And so what it appears is that when they were extracting it, they were just creating these molecules. Now, you're probably going to ask about humic acids. Those, again, are something that are created for the products that they go into. And in some cases, in a lot of cases where humic substances are mined from, it's a substance that's, as far as I understand, similar or on its way to becoming coal. It is organic material, and it has been naturally decayed, but it's under extreme pressures and extreme time that has created it. And so these humic substances, when combined with nutrients, or when combined with compost or other things, they still can have an effect, and they still can be beneficial for the system. But it's not the way, at least that I have seen it portrayed, is that we're just adding stuff that would have been there anyways. They are something new added to the system. So this has come up with, we'll just transition here to what I learned 2 years ago. So I learned this during the pandemic. There were a lot more online presentations and online material available, and through the professional organization that I'm a part of, the Professional Agrologists, there was some presentations over the past few winters on advances in agriculture, and of course agrologists cover oil field reclamation or any reclamation work, so it was in that too. But there was a presentation on the new understanding of how things worked, and the new understanding is that there's a microbe for every molecule. And so we still have the living portion, and we have the dead portion of organic matter, which is the stuff that we can actually see. But then there's this particulate organic matter, and the line is not very, the line is maybe a little fuzzy, or at least a little somewhat arbitrary, but I think soil scientists would tell you there's more to it, but it's basically a certain sieve size or certain size of organic matter. And it can be anything from just like little bits of a leaf to spores to anything. But it's very tiny stuff. It's stuff that you wouldn't be able to see with your eye. You'd have to see it under a microscope. And then there's this mineral-associated organic matter. And now this mineral-associated organic matter is down to the molecular level. It's stuff that you would not be able to know what its original structure was because it has been broken down by microbes. And as the name implies, it's associated with minerals. So it's on the minerals, or it's part of the soil aggregate, kind of that whole system down there. Now, on to what I have learned this year. There was a presentation or a training, or an organic agronomy training by Dr. Martin Entz. He covered some of the new theories on organic matter, and it is in your resources for you to look at. I've also, it just happened that there's a paper that only came out, I think it was February 6th, so covering a lot of these new theories on organic matter and what the controversies are. So it can get very confusing very fast as you get into this, and there's huge debate in it. Now, one thing I have heard over time, or over the last few years, that isn't necessarily new, is that root exudates make the MAOM, or mineral-associated organic matter. You might have heard people say that the only way to make organic matter is to grow cover crops because the root exudates feed the microbes, and those are the ones that make the long-term organic matter. So that is one thing I've heard of. There's people that say the residue doesn't contribute to soil organic matter, that all the residue ends up as CO2, which in reality, a lot of our the organic matter that we see always ends up as CO2 because it's always cycling. Some estimates are that it's anywhere from 80 to 90% of everything that's produced ends up in soil organic, or as carbon dioxide, but that's because carbon is energy in the system. It's not only a building block, but it's energy. And a couple things too, I'll just point these out. Spatial and energetic inaccessibility. Again, this is a very, very new concept, or at least to me it is. It's the idea, you can think of it as if the microbe can't get to it, then it's more persistent, which when we have to think about a soil system, if you're a mineral of soil, or a clay particle or a sand particle, if the microbes on one side of it and the food or what it could eat is on the other side of it, that's like being on the other side of the world for us. So if you can't get it together, then it's not going to break down. Energetic, and I think this is the idea that if you don't have the microbe down there and it doesn't need it, or I guess if it can find a better pathway, it's not going to break something down, but then when it really needs it, it will break it down. So that is the main coverage of the how soil organic matter has been seen, or how it is being seen in the soil system. Now let's get into something a little more practical, a little bit more that what we can see. Soil aggregates, regardless of how organic matter is formed, or regardless of the process, because the details are still being figured out, we still know that soil aggregates form. They are, the more we have mycorrhizal fungi and earthworms and such moving around in our system, the more these are created. They're created somewhat unintentionally. They are, as these things grow through the soil, they end up gluing the soil together, which has some function for them if they're doing it. But even long after they're dead, it helps to hold the soil together better for us. And as these structures are created, they have a byproduct of helping to slow erosion, both wind and water. It can help the water to infiltrate better because we have better pore space. And it can help the water to absorb better or hold onto the soil better because there's more smaller areas for it to grab onto. And then it can also release to the plants better. So anytime we can have these soil aggregates forming, it's a benefit to us. And in recent years, it appears that these soil aggregates, or the stability of them, is one of the greatest indicators of soil health. I have seen this there was a tour with Dr. Abby Wick this past summer that I was able to join on when she was touring through Alberta. And that was the big thing she was looking for. We had a bunch of soil health tests, like a big suite of soil health tests, and we were out in the field looking at things. But how it was intentionally done, where we looked at the soil first, decided how healthy we thought it was, and then we looked at the numbers. And to her, some of the times the soil health tests, or what all the different parameters were in them, didn't line up with what we saw. And to her, aggregate stability is one of the key indicators, because it's not only a great thing for the soil, it is also proof that the organisms are working in the soil. Now, another key thing about soil aggregates is that it would be unnatural if they stayed together permanently. Sometimes we think that we need to build them up and build them permanently, but they're always changing. They're always moving, getting moved around as roots go through, as earthworms go through, or as other soil critters move through the soil. Then they're always getting broken up or moved around. And the way I would think about it is, if we always had these soil aggregates, if they never broke down, we end up with like a porous rock down there, or a hard structure that's just going to be like pebbles. And in fact, if you've heard of a earthworm in Minnesota that is causing a lot of problems in the forest floors, it actually works too good at making aggregates, or I guess it's the worm castings, but then because it's breaking down the forest material so fast, it actually makes like this a soil that's very, I guess it's described as like coffee grounds. Like, it feels, in some ways it feels, oh, this is a great soil, it's got nice tilth, but it has no structure because it's just all these little pebbles of aggregates and earthworm castings, and it's causing a lot of problems because some of the trees can't root as hard, or can't root. They get blown down easily, and so it's something where we have to think of that. Aggregates aren't something that we need to constantly keep, or we need to kind of get more and more and more. They're constantly being created and destroyed. So this is where, as we get more deep into the tillage, as long as we're not destroying them too much, or as long as, if we have good aggregates to begin with, we're not going to be destroying them all in one pass. We can meter out what we're doing, and match the amount of tillage to the goals that we are trying to reach. Okay, let's get into the factors that determine soil organic matter. Now, I did talk about the different types, with our living and dead, our particulate organic matter, our mineral associated organic matter, and all the different theories on how it is actually formed. But the reality is, all that we can see, or a lot of the work on observing organic matter formation, is still valid. We're looking at the end product. We don't have to know the details to make it work. As we learn the details, we might be able to fine tune the system a little bit better. But I think we can still look at the overall picture without getting lost in the details. So texture is one of the biggest drivers of how much soil organic matter you can have in your system. In North Dakota, in a book called the Midwest Tillage Guide, which the links will be for, so you can look it up later. They have the numbers that in a sandy soil, 1 to 2% is all we can expect. In a loam soil, which is a mixture of the fairly even mixture of the sand, silt, and clay, 2 to 3%, and in a more clay-dominated soil, 4 to 5%. Now, the reason for this is it's just the places, and I guess this is where the spatial theory of soil organic matter can make sense. In a clay soil, there's just a lot more little tiny spaces within the clay particles where soil organic matter, or I guess dead necromass or dead microbes or anything, can sit and not be touched by another microbe. So it's protected. Whereas in a sand, the particles are so large and organic matter is floating around, is sitting, it would be on the surface of these sand particles, and it's very easily accessible. So even regardless of tillage, just even in a natural system, you just can't build up organic matter on them. This is why beaches are, you won't find much organic matter in a beach sand. And so this is just a factor of the system, is that no matter how much you try, you can't build up the same level of organic matter as you could if you had a clay soil. So on your farm or on particular fields or within particular fields, just recognize this as you have different areas. This is a limitation, or it's just the reality of how organic matter is going to build. Now, you probably heard those organic matter levels, and you've thought, well, it gets higher as we go further north and into our black soil zone. And this is where moisture and temperature have the impact. So I'm from the brown soil zone. We have very little moisture and we have high temperatures. Whereas we go further north into the black soils, there's more moisture and the temperature is less, or at least there's a longer season where it's cool and wet. And so when you have those factors, it's basically you have to think of soil organic matter is a carbon flow, or as a flow of things, not something that just builds and builds and builds. So as you have more moisture, lower temperature, things slow down. So then you basically keep some of that organic matter around in your system longer. Whereas down in my area, in the brown soil zone, then when you have less moisture and a higher temperature, then there's more opportunity for organic matter to get used up. And you also have to think that in a soil, we might look at it as dry or not having much moisture, but if you get down to the individual particles, bacterial or fungal level, they can find moisture that we can't even see or feel. So when the temperature's up, they can use it. So it gets used up faster. And of course, there's another factor too, is that when you do have more moisture, you have more chance of growing things. in my area, we have less chance of growing things. So then there's less inputs into the system in the brown soils, and there's more inputs in the black soils, and there's more opportunity or slower decomposition. So saturation point is a reality of it. Is another key concept, is that you'll always reach a point where decomposition matches the input. And this is where we have to think in our soils in Alberta. They developed over 10,000 years. And even if you just think in what has happened to them in the last few thousand years, it's a process. Some years there'd be more input, some years there's going to be more decomposition, but they reach a point where you put more and more in, but then you also increase decomposition. Now, you've probably heard of Gabe Brown and his massive soil organic matter increases. It would appear in his system. So if you think about his system, he is the only thing he exports off his land is the cattle, or at least in the main thing that is exported off the land is the cattle. And so when you can grow massive amounts of grass and then mob graze it, and then you are just putting huge amounts of stuff back into the system, that's how he has built up his organic matter. Now, it seems to be increasing and increasing, at least according to what he's saying, but there will be a saturation point where the more you put in, then the more it decomposes. If you get to the point where you don't reach that, then you're going to end up with peatlands, like what we have up in the very north part of the province and bordering onto the Arctic. And I can tell you that that's not the kind of soil that you want to deal with. It comes with its own challenges with high organic matter, but a lot of stuff not available, and pH dropping typically in that. So when we are looking at soil organic matter, the final thing here is we reach a new equilibrium. We always are reaching an equilibrium on things, and this is one of the things that that's one of the criticisms that I have against the carbon payment programs, or at least, and I think it is coming up in soil science, and I think the problem is that the people that have pushed the idea of carbon credits have either ignored, or at least they're not focusing on decomposition. So the more you can't just keep adding and adding and adding. You reach a new equilibrium because the more you put in, the more you ramp up the biology. And that's not necessarily a bad thing. It does lead to a more healthy soil, but you do reach a new equilibrium in things. So now I want to shift to tillage. On the prairies, we would have had tillage, natural tillage, even though we may not necessarily think of it. The buffalo would massage the top of it, as it's been pointed out, with their hooves, and when they're rooting around looking for fresh grass. They also have their wallows where they apparently would return to over the years or over the centuries, where they've actually just pushed or even just pulled out the vegetation over time as they've did that. They've made little holes in the ground and such like that. But so that would be the surface. There would always be this changing of the surface. We have the gophers, which probably none of us really like. especially if you've ever twisted an ankle going into a hole. But they provide some of the natural tillage in the prairies. One of the interesting ones that I had never thought of until I read about it in a book. Ants are probably our natural tillage of the prairies. They they wouldn't do much in any one year, but it's estimated that they could till a soil over a period of 100 years. They could completely move it around. Now, earthworms, they are new to the landscape, relatively. They've been here for many centuries, but they're not necessarily, they're not native to the area. I believe that it's thought that they might have been here prior to the Ice Age and then were one of the species that got wiped out, so they may not necessarily be entirely foreign, but they are something new to the landscape. And I hear people say that they're a good indicator of soil health. As I'd said earlier, if you get the wrong species in there and they start doing things too well, they can be a detriment. So I've heard some people say, "Oh, the more the better. The more earthworms, the better it is. It doesn't matter." But no, there's a point when you could have too many earthworms, and they're also not necessarily the greatest indicator of soil health just on a just digging, because you could dig a soil and if it just happened that it's moist and the right temperature, you're going to see a lot of them. But if you come at a point when they're deeper down or they're we all know how spatially different a soil is. They could just be in a different part. So they are good if they are at levels that are helping your soil. Good or bad, I think they're good to have around, but just be mindful that just because you don't see earthworms doesn't mean your soil's not healthy, or seeing earthworms doesn't always mean that it is healthy. And of course, we are going to talk about human activity with tillage. It has been used for thousands of years in all forms of agriculture. The indigenous in the prairies used digging sticks. As far as I've been able to understand, the furthest north was in what's now called the North Dakota, where there was some forms of agriculture used, but they all used some type of way to dig up the soil to plant the seeds, or use buffalo bones to break up the grass or cut the grass out, or making hoes to hoe out the weeds. But tillage has always been used. Now, in that particular system, the soil is still what we would call degrading, in the sense that once you start agriculture, it always does diminish in productivity over time unless something else is brought in. This was something, if you have a chance to read Buffalo Bird Woman, there's a book called Buffalo Bird Woman's Garden, and in that book, she details how they farmed, and she admitted that always the first crop was always the best, and then it diminished over time. But the difference was they could move on to a new area, and that area could regenerate over the centuries before they come back. Whereas for us on the colonists, it was thought that there isn't that we could just keep tilling and bringing up plant food, and or we could always keep tilling it, and that there wouldn't be a detriment to the soil. Now, if we could have tilled, used the soil for a while, let it go back to grasslands for 100 years, I kind of wonder if it would have been fine. It's hard to say, but it's unfortunately it's an activity of humans at large scales. Every human civilization has degraded its soils back to ancient times. So hopefully we are the ones that can recognize it before it happens and get ahead of it. So why do we till? Now these are the reasons, or this is what I have come up with on my list. Maybe you'll have more. So releasing nutrients for crop growth. Now maybe you don't think of it that way, but you are doing that. Now if we're doing it in a sustainable way, then that's fine. This is the way that the early settlers grew their crops. This was the fallow system where they would till the soil. It would break down organic matter, release nutrients that they could use for the crop. They grow their crop and then fallow again. They weren't putting anything into the system. They were only taking from it. So now whenever we till, we will be doing this, but that's not necessarily a bad thing. That's our slow release fertilizers or nitrogen, phosphorus, whatever is built up in some of that. It's nice stable form, and then the crop can use it. Now when we do till, a lot of the reason is to make what we consider the ideal seed bed. And making the ideal seed bed is, in a lot of ways, the reason for this is that whatever we grow has adapted to us making the seed bed for it. Most of our crops are not something we can just put on the surface and rely on it germinating from there, or rely on other things planting it for us. They're reliant on us putting it in its ideal seed bed. So well, we have to put it in the ideal place, but then we also have to have the soil in the proper form so that it can root and grow rapidly. Now, probably one of the biggest things that we till for is controlling the weeds. And that's something that is ongoing. It starts right from the beginning of the year through the crop season, and then at the end of what we can do. And we're going to come back to that a little bit later. So terminating perennial crops, tillage is really the only way that we can terminate a perennial crop, especially thinking alfalfa or any of the grasses. I mean, there might be some ways that can hurt it and set it back, but it is the way that we can terminate them. And cover crops. Whenever we put in a cover crop and want to terminate it, the best way to get a cover crop or get the best use of it is to terminate it when it's near flowering, or in the very least before it sets any seeds, before it starts putting the energy above ground. We want to terminate it to keep all its built up energy below ground. And so tillage is a way of doing that. And it is a way of getting those cover crops, the nutrients, put back into the system in a more, it speeds up the process if we can till them in. And of course, if we're adding in manure or compost into the system, then tillage is going to be essential. In a grazing system, all that manure sits on the surface, but there are organisms that pull it down quickly, and there are plants growing, and there's plants nearby that prevent it from running off the soil. But if we have manure or compost, we need to get it into the soil somehow. So tillage is a way of getting it in there. So I grew up in the 80s and the 90s, and no-till really developed over that period, and through the last 2 decades as well. Now, there's been a lot of work on trying to make no-till work in organic. My thoughts are that I don't think it's the holy grail or the ultimate goal of getting organic into a no-till system. The reason why I think of this is I think that instead of thinking of no-till as the goal, I think the goals should be to minimize erosion, either by wind or water. So your goal might be to increase or maintain your aggregate stability, or maybe it's your goal might be to prevent weeds so that you don't have to come around and kill them. Those are all things that you can try to. Those are goals that then you can say, okay, what can I do to how can I use tillage or the lack of tillage to reach those goals? So minimizing erosion, obviously we can look at having living plants all the time, and if we can have those plants adapted or using the in the system where we don't have to be using as much tillage, that's a great thing. If we want to maintain or increase our aggregate stability, this is where getting the proper cover crops in place, and maybe relying on things like winter kill to kill them rather than tillage is a way that we can increase our aggregate stability without having to use tillage. And preventing weeds, this is probably the biggest one, is using cereal rye to, or as it's more commonly called here in Canada, fall rye, to prevent weeds. So probably many of you have heard of the no-till organic systems that are being developed or being tried out. The biggest ones are with Dr. Aaron Silva in Wisconsin, Dr. Martin Ince in Manitoba. The basic concept is to get a rye crop growing and get it so big that it outcompetes all of the weeds, which it can do because it grows in almost any weather, and then kill it, and then quickly get your cash crop in there to grow. The biggest problem is the biomass. So in Wisconsin, even there, they struggle to get the amount of biomass ahead. They still have to be killing it in June, because the only way to kill rye without tillage is around pollen shed time, is the roller crimper, and that seems to be the best way of killing it. And then you have to get your crop planted. Aaron has said 5,000 to 8,000 pounds per acre of biomass is essential, which is a lot. And there's a lot of nutrients in there. There's a lot of nitrogen tied up in there, a lot of phosphorus, a lot of everything, and even carbon tied up in there. So to be successful, you have to have a system that can buffer that amount of nutrients while you grow your next crop, which is typically the one where it seems to work the best is soybeans. And then of course the other problem that can come from rye is that it is allelopathic, and you have to plant crops that aren't going to be affected by it. Dr. Martin Ince has some interesting systems with rye and some other covers in there with hairy vetch, but the best success was not thinking of it as a no-till system, but as a no-till phase. Once every 5 years was the best success from it. Now, to make no-till work in Alberta, no-till organic, and rely on the crimping system, I think is going to be very challenging, because even, as I said, in Wisconsin, they're not planting until June, or they can sometimes go in and plant the soybeans ahead and then crimp later, but they're warmer there, and they have their black soils, and they can make it work there. But it's going to be a challenge in our area. And unfortunately, every time, like when they have been successful in making it work, in being able to control all the weeds, or at least most of the weeds, not have to do any stuff after, but it's never got better yield than a tillage system. So I think it's something that can always be worked on or developed, but know that it's not the holy grail, at least in terms of getting organic that way. Now, I do want to bring this up because there are new technologies coming out that may enable reduced tillage, maybe not no-till specifically, it's hard to say, but they could help to reduce the amount of tillage, both in conventional and in organic systems. I guess in conventional, there's already a fair amount of no-till success, but it is all about herbicides. And with that not being as great of an option in organic, then we have to look at where these could fit in. So as these systems are able to recognize the crop and recognize the weeds, we have potential. Or if you think about it too, if it could recognize the cover crop and kill the cover crop while the before, or set back a cover crop and let the cash crop go ahead, it might work. So we have robotic weeders. They are probably a long ways away from field scale, but they are possible in vegetable production. But they're expensive. The technology is always evolving, and it's probably going to take large acres for them to make sense. But as they come along, that's a huge thing. Laser weeders, maybe they fit into the same category as robotic, but it's a similar thing, except that you don't have to have something physically touching the soil. Now, sprayers. These are a big one that are coming out in the conventional side, where we have these sprayers. The best adapted ones are the ones that are actually being commercially used in southern Alberta right now, are green on brown. So when going across a field, instead of spraying broadcast across the entire field, each nozzle will only fire when there's a weed there, when there's something there to control. And so those are being used, and farmers are having really good success with them so far, because they can cut down their herbicide use by 3, 4, 5 times. There's a lot that they can do with it. Then the organic system, where I see this as having potential, though I think the cost on these sprayers could be too much. There are limited number of organic herbicides, and I know when I've looked into them, they're very expensive. They take high water rates or high usage rates to use, and they do take a lot of coverage. You have to get a lot on the weeds. So this is a possibility, that instead of at broadcast levels, or at using them at using these organic herbicides at scales of having to spray it across the entire field. It could be just targeted to what you're going after. So I think there is potential there, but it's something that we can look at in the future. The big one is really going to be when it can recognize a crop and only spray the weeds. The inter-row weeds are still going to be a problem, but who knows what's going to be developed in the coming years. So this is a way that we could reduce tillage in the future, but maybe not there yet. But as we go into the final activity of the day, perhaps you can dream about using this or see where it could fit into your system. So let's come back to present day and what we can do. So tillage intensity. There's many different ways that we can look at this. So in a rotation, perhaps once in 5 or 8 years, you need to plow in forages, and maybe, or along with that, or at a different time, dealing with perennials. Now, yes, that is going to be a major impact on your carbon levels, but it's not going to hurt them as much as you might think. So a lot of what it does is it's going to take a lot of that, some of that particulate organic matter, the smaller, finer things that we can't see without a microscope, and it's going to take all the leftover materials and mix it all together and get it in the perfect place for microbes to use. And so yes, you will use up a fair amount of your carbon at that point, but it's more that you sped up the process. If you are deep plowing every year, I think that's a problem. That's too much tillage. If this is a once in many year thing, then no, I don't think it is a problem, because you're solving a problem. You're getting the forages back into the system, or you are dealing with a perennial problem. And the perennial problem could be even going with multiple passes to cut them back at whenever they grow 3 to 5 leaves. You keep cutting them back and keep depleting their reserves. Within the season, there's different amounts of tillage across the season, so spring, summer, fall. So this is where we can look at the intensity of when you're doing it, and this is something that could fit into rotation, where maybe there's a crop year where there's a lot more spring tillage. There's maybe some years where there's more fall. Some of them might be more intensive in the summer. So we can look at when we're doing the different amounts of intensity of tillage. Now, aggressiveness. This is where I think we need to really factor this in. A tine weeder versus a rototiller, very, very different in what they're doing. I see in my area, there's a lot of people like using power hillers for their potato rows, and they make these nice. Well, they call them nice. I don't think they look nice. Perfectly formed potato hills, but it just pulverizes the soil. And so when you're doing that is definitely, that's breaking up aggregates. When you're using a tine weeder and you're just a tine weeder, or any of these early season weeders that can like rotary hoes and harrows and stuff that are trying to take out the weeds and preserve the crop, they're only going a small distance in. They're doing very minimal soil disturbance, but they're just trying to take the weeds out. But if you're using a rototiller or really deep tillage a lot, that's different. The frequency, so many small passes or quick passes, early season, and then we're letting the crop grow for the year. Again, yes, you will be taking off some of the carbon, but you also have to look at your aggregates. If you can measure your aggregates, if you're not making a difference or a large difference in breaking up aggregates, then again the cost in this, or the what it's doing to your soil carbon, is not as impactful. And depth, this is the other factor I have in it, shallow versus deep. This also fits in with a lot of what I've already talked about, but on the other hand, I think we also have to think about this too. A frequent, say like once a week for a few weeks, pass of rotary harrow that is a rotary hoe that's only going an inch deep or so, or more on the surface, and it's not covering the entire surface. That's different than a deep tillage where you're going further in and inverting the soil. So if you think about the depths of the soil, or how the soil, if you're looking at the soil profile, yes, you are impacting this top portion, but deeper down, the mycorrhiza fungi and the roots and everything is totally fine. It's no different than the buffalo scratching at or walking across the surface. So when we're looking at tillage, this is where I think we can look at all these different factors in the intensity, and then design our systems so that we're not doing the same things over and over, and we're using multiple different things within the system. I would love to have a formula as to where you could plug things in, but I just don't think that would. If you could plug in everything you did and come up with something, and maybe that exists, maybe you can tell me about it. But I think it's more something that we just have to observe in time. Is we have to look and see, are we impacting the aggregates too much, and so what is the net impact? So if we still have aggregates afterwards, we're going to break up some of them. But if we've accomplished a goal, then the tillage is most likely worth it. If we didn't do the tillage and we end up with either weeds getting out of control or not a very good establishment of our crop, then maybe that's a worse situation. So once we look at the intensity of the tillage and try to lower the intensity or vary up our intensity over the course of years or seasons, or within a particular time period, or in terms of the depth, we want to look at mitigating the effects. Now, the biggest thing you can do is have a plant growing right away. And I have always thought of this. I work in a lot of potato production in the southern Alberta, and of course there is a lot of tillage with this. Even if you try to minimize your tillage, there is tillage, but we can kind of supercharge the system if we always think of trying to get a plant growing in to make up for the whenever we have to do deep tillage. Now, early season, if you've got your crop growing, then that's fine. You've got another plant growing. Or even if you back up a little bit, say if you're doing some tillage before planting to try to take down a flush of weeds, or even try to get ahead of it with tilling before you even see the weeds come up, don't worry about it, because you're soon going to have a plant growing. Your early season, you've got cool soils, there's not a lot of biological activity. You don't really have to worry about the microbes eating up your organic matter at that point. So do your tillage then, and then get your crop growing. In season, if you're doing tillage, inter-row tillage to take care of weeds between the rows, and you've got the crop growing, you're fine. The main thing is that you have something there so that the plants are feeding the microbes and they don't have to start going into the organic matter to eat. Now, if you have an amendment on the soil, which could be green manures, so you would have just had a plant growing, or animal manures or compost, what this does is it provides the nitrogen so that the carbon isn't hacked or isn't used up. And I know this can get into an endless debate as to whether nitrogen builds organic matter or whether it destroys it. But if we just take a step back and think about it, in the original fallow systems of the prairies, the reason that the organic matter kept going down was that they were not putting nitrogen into the system. If you just till the soil for a year in a fallow system, and then you plant a wheat crop and grow it, and then you just keep doing the same thing over and over and over again without replenishing, then the microbes and organisms underground have no choice but to go into the older organic matter and use it, and then in the process release the nitrogen. And so even as I'm starting to understand these newer systems of organic matter creation, this could be the energetic side of it, where if you don't have the nitrogen there, or don't have the nutrients there, or what the microbes are looking for, they go looking for it in what they can find. But if you have nitrogen there, which could be in the form of green manures, animal manures, that is a less energy intensive pathway, so they'll use those. And we want them breaking those things down because we want that available for our crop in the following year. So those are the two key things. If you can avoid it when biological activity slows, so a dry season or a dry period, a hot period, a cold period, that can mitigate some of the effects. And the reason for this is that the mycorrhizal networks, if they're left intact when the heat comes or when it dries out or it gets cold, they can revive a lot faster than when not. So if you can avoid it, but again, mycorrhizal networks, they recover. They're resilient. They're used to things happening. So we can always get them back in place. One little very, very interesting thing is that the mycorrhizal spores, in case you're wondering, well, if I kill all my mycorrhiza, then I won't have them in my system. A really interesting study I heard of, somebody put spore traps up on top of skyscrapers in Chicago, and they were able to find these spores year round. So somehow they traveled the whole globe year round. There's always things moving around. So biology can always be restored. We don't have to worry about killing the soil. It can always be restored, but if we can avoid it when the biological activity slows, and if we can have a plant growing, and if we can have an amendment that provides the nitrogen, we're good. So this is kind of a summary of what all I have been talking about in this last section on tillage. I like to think of a lot of things in return on investment. And what that has come down to is that you should always be solving a problem. So I have examples here: a better seed bed, quicker use of organic amendments, controlling perennial weeds, etc. So if the tillage is going to be a tool that is going to help things to grow better over the next few years, then by all means do it. You have to think about, on the second point, what will happen if you don't do it. So if you have a compaction issue, maybe a tillage pass where you can break that compaction and then quickly get another plant in there to prevent it from recompacting is going to be better than trying to grow tillage radish or something that's going to take multiple tries or multiple attempts at getting it to work. Or if the weeds are always going to be taking over, if you can break up that compaction, get your cash crop working better, then that's a better outcome. And then say something like compost. If you don't till it in, you have the risk of it either getting eroded off, washing off, or just the fact that it's not going to be as readily available to your crop. How do you know when it's too much? So you might be solving a problem, but you might be making a bigger problem. If what you do causes it to blow or flow away, that is too much. If you end up doing tillage and you have puddling of water, so in other words, you've sealed the top or it's not letting water get in, again, probably you have did too much. But these are things that are you have to judge every situation for. Now here is where we're going to get interactive. We're going to work together. We're going to work on a problem or maybe a few different problems depending on how much time you have, and take everything that we've learned so far in this workshop and start applying it to your farm, because we want you to go home and either be able to change something or realize that what you're doing is working, and then be able to make some changes in season as you see things and kind of adapt. So I advise you to get creative. You might look at something and say it's too expensive, but could you share it to offset costs? Is there a business opportunity for you to start custom using a machine to pay for it? Or could you adapt existing equipment to do things in a little bit of a different way? So you can work through all of these different these questions, or go back through the material and adapt that way. You could also, if you're really curious about some of those new systems, the robotic weeders or the laser weeders, or the new sprayer systems, maybe have a discussion on how that could potentially work on your farm. So with that, it's time to do the workshop and enjoy the process.